Dear students, today we will be discussing a tutorial on thermal energy storage. In the tutorial, we will be specifically discussing on the solar pond power plant design. So, straightway we can take the analytical solution for the annual average temperature variation in a solar pond, which was given by Ravel and Nelson. Okay. So, this is the relationship like T3 dash minus TA dash, or we can say bar. So, what does it mean? T3 bar, which is equal to annual average temperature in the lower convective zone, and TA bar, which is nothing but annual average ambient temperature, and Hg bar is nothing but annual average global radiation. Then Kj dash is equal to Kj by cos of theta 2, where theta 2 is the angle of refraction corresponding to an effective angle of incidence taken on the equinox day at 14 hours local apparent time at the location under consideration. And L2 is the depth of pond at the bottom of the non-convective zone. And Q load bar is nothing but annual average heat extraction rate. And K is nothing but thermal conductivity of water. Okay. So, this is the area. Okay. So, we need to find out the area, okay, if we know other parameters, right. And Kj values are already discussed, and we will be using those values in solving one of the numerical problems. Ag values also given to us at different wavelength. So, straightway you can use it, and tower values has to be calculated at incidence angle, okay, which is specified for a particular location, right. So, this analytical solution is normally used for space heating applications, and this analytical solution is one of the simplest solution and is useful for calculating the average performance, and also it is useful for estimation of area of a solar pond for a given requirement. So, for a given location, heat load and annual mean extraction temperature, there is an optimum value of L2 corresponding to which the pond area is minimum. Okay. So, that we need to calculate, because it is one kind of optimization problem. Okay. At what length we will get the optimized parameters. Okay. So, if we can fix it up, then accordingly we can design other parameters. So, without delay we can start a numerical exercise. The exercise goes something like: a solar pond located in a place having latitude and longitude are 28 degree 35 minute north and 77 degree 12 minute east is to be used for supplying the heat energy input for a low temperature Rankine cycle power unit using ammonia as working fluid. The unit develops an output of 18 kilowatt, has an energy conversion efficiency of 8%. So, Rankine cycle efficiency is given as 8% and requires its energy input at an annual mean temperature of 82 degrees C. So, I will draw the pond and I will designate which location we want 82 and what is 8% efficiency. Use the Ravel and Nelson analysis to calculate the pond area for values of the depth L2 varies from 1 to 3 meter. And we need to show that area is a minimum for a particular value of L2. and we need to plot the variation of area versus depth of the pond. The radiation and ambient temperature data of the place given are as follows, like annual average daily global radiation is 19520 kilojoule per meter square per day, and annual average ambient temperature is given as 25 degrees C. Okay. So, we can use the analytical solution given by Ravel and Nelson, right. So, this correlation we can use. So, first let us draw the solar pond. So, we will have sun here, sun ray will fall, okay, and we will have this kind of pond. Okay. So, there are 3 layers already we have known. Okay. So, this first layer is known as surface convective zone, and second layer is known as non-convective zone, and third layer is known as lower convective zone, right. And this is applied to reduce the heat losses. Okay. Of course, this has to be some kind of insulation kind. Okay. So, solar radiation is falling here, and data given to us is something like T3 bar, which is nothing but 82 degree C, right. So, what is this temperature? So, maybe we can think of this kind of heat exchanger here, and we will think this kind of heat exchanger. Okay. And this is connected to here, and here we want 82 degrees C. Okay. So, already this is given, and we will have this Rankine cycle, right. In the Rankine cycle, what happens? We will need some kind of working fluid. Okay. Since this is a low temperature operation, then we need some kind of refrigerant, okay, or organic fluid, right. So, what we will get, this is 18 kilowatt. Okay. So, this is turbine, this is condenser, this is pump WP. So, pump work is neglected here, and this is the heat exchanger. So, this hot water goes in the heat exchanger and exchanges it with this organic fluid, and then fluid will be evaporated or refrigerant will be evaporated like ammonia, what we have used in this setup, or maybe other refrigerant R22 can also be used. Okay. So, it will evaporate and pressure will rise and it will expand in the turbine and electricity will be generated. So, it is given that 18 kilowatt electricity is generated in this setup, and this is a condenser and pump, and it circulate again and again, right. So, I will now write down what are the information given to us. Okay. So, this efficiency, Rankine cycle efficiency, so eta RC I will write, which is given as 8%. Okay. And ambient temperature, which is average of the year, it is 25 degrees C, right. And also we know the annual average global radiation, which is given to us, annual average global radiation, which is designated by Hg bar, which is given as 1950 19,520, right? So what is given, you can see here, 19520 kilojoule per meter square per day. Okay, this is kilojoule per meter square per day. Okay, so we can convert it to watt per meter square. So if we will do that, then what we need to do? So 19520 multiplied by 10 cube, it will be joule now. Then it is in days, so it's a 24 hours, and then 3600. Okay, so this will give Hg in watt per meter square. So this is something like 225.92 watt per meter square, right? So this is important. We need many times this information. And also we know power output, which is equal to 18 kilowatt, right? And efficiency of the Rankine cycle is also given, it's a 8%. So eta Rc, which is equal to 0.08, which is equal to, this is power output to the input energy. Okay, so input energy or power input, or I will write P input, right? So this is nothing but Q load or annual average heat extraction. So this P in or P input, which is equal to Q load, will represent, which is nothing but P output, which is power output, and this will be something like 0.08. Okay. So if we substitute the value of power output to be 18 kilowatt, okay, and this is 0.08, so this will be equal to 225 into 10 cube watt. Okay. So this is nothing but annual average heat extraction. Okay. This is annual average heat extraction. Okay. So this we can represent like Q load. Okay. So Q load is known now, and Hg in watt per meter square is also known to us. Now what we will do, we will calculate theta 1. Okay. So that means let us calculate the values of the effective angle of incidence and reflection. Okay. So this angle of incidence, which is represented by theta 1, and this is represented by theta 2, right? And these two values have to be obtained on the equinox day. Okay. So equinox day, that means delta has to be equal to 0. okay, and at 14 hours, okay, 14 hours, which is LAT, okay, so local apparent time, right? And also we know the expression for angle of incidence for horizontal surface, and that has to be for horizontal surface. Okay. So, this is something like cos theta is equal to sine of phi, sine of delta, then cos of phi, cos of delta, then cos of omega, right. So, if we substitute, say maybe 1 we can write, the value of delta is 0, okay, then equation 1 implies cos of theta is equal to, so here sine 0 is 0, so this expression will be 0, then this will be cos of phi, then cos 0 is 1, so it will be cos of omega, right. So, this may be equation 2. Also, we can calculate the latitude. The latitude phi we can calculate from the given data 28 plus 35 by 60. So, which will be equal to 28.58 degree, okay. And what will be the omega? So, this has to be calculated 14 hours local apparent time. So, that means every 1 hour. So, if we consider this, and this is solar noon, so this is 12 hours, okay. So, every 1 hour, so this side means 11 o'clock if we 11 o'clock if we consider, then this will be 15 degree, right, and this will be positive. So, other side, so it may be 13 hours, so it will be 15 degree, but it is minus, right, because afternoon, and at 14 hours, so it will be minus 30, right. So, that is how it is minus 30 degree, okay. So, omega is also known, then phi omega is known, and we can use the equation to find out what is theta, and this theta is nothing but theta 1, okay. So, equation 2 implies then cos of theta, this theta is nothing but theta 1, okay. So, cos of phi is 28.58 degree multiplied by cos of minus 30 degree, okay. So, if we do the calculation, then theta 1 is found to be 40.49 degree, okay. Now, what we need to do? We need to find out tau r, okay, at this condition. So, already you know the expression here what we have shown. So, this tau r. So, this need to be calculated, right. So, let us see how this can be calculated at that angle, right. So, already we know the Snell's law and we know this chart, okay. If we know the angle of incidence, then from that we can calculate what will be the tau r, right. So, from this Snell's law, what we can write, sin theta 1 divided by sin theta 2 will be nothing but the ratios of refractive indices, which will be something like n2 or mu2. Okay. So, maybe n2 I can write here, n2 by n1, which is nothing but 1.33, right, because this is the surface convective zone and this is the interface between air and water, okay, or liquid. Okay. So, we know the refractive indices and from that we can calculate the ratio, which is equal to 1.33, right. And here already we know theta 1 and we can calculate what is theta 2, right. So, sin theta 2 will be sin theta 1 by 1.33, and from here we can calculate what is theta 2. So, this theta 2 is equal to 29, because this will be sin inverse of this value. So, if we calculate it, it will be 29.22 degree. Okay. And also we can calculate what is cos theta 2, because this will be requiring in order to calculate Kj. Okay. So, this is something like 0.8727. Okay. And why this is important? Because we need to calculate Kj prime, which is equal to Kj by cos of theta 2, which is angle of refraction, right. So, this Kj, because J will vary from 1 to 4, means K1, K2, K3, K4. So, everything we need to consider. So, let us prepare for that. H7 then 27. Okay. So, these values are also calculated now. Okay. Now, we need to calculate tau r. Okay. So, we need to use this table, and as you can see 29.22 is theta 2, and then theta 1 what we already got is, so I will write theta 1 here. Theta 1 already we have calculated, it is 40.49 degree. Okay. So, we know the values at 30 and 45. So, we need to calculate at 40.49. So, how to calculate it? By using interpolation, right. So, by using interpolation, so tau at, or this is tau r at 40.49 degree, which is equal to, first what is the data? So, this data, these two datas are required. So, from 30 to 45 it is decreasing. Okay. So, we have to use negative sign, minus, then 0.979 minus 0.973 divided by 45 minus 30, okay, multiplied by 40.49 minus 30. Okay. So, if we do the calculation, then tau r is found to be 0.9748. So, which is in between these two. Okay. So, this tau r value at 40.49 degree is something like this. Okay. So, we need this value for calculation, right. Now, we have been given, so this we need to apply, that is why I kept it here. and what is given? Thermal conductivity. Okay. So, thermal conductivity K is given, which is equal to 0.648 watt meter Kelvin. Okay. Now, we know this expression, analytical solution, okay, and straightway we can use the calculated data and given data, right. So, using the data, this equation maybe we can write as 3. Okay. So, we know the value of T3 bar. So, this is 82, okay, 82 minus TA is 25. So, we can substitute 25 here, which is equal to tau r, just now we have calculated, which is found to be 0.9748 multiplied by Ag, we have already calculated in terms of watt per meter square, which is equal to 225.92. Okay. And K value is given to us is 0.648. Okay. And now we need to use many parameters here. Okay. So, here is a, so I will write 1 to 4. First let us learn how to express it. A1 K1 this. Okay. So, this 1 is J is equal to 1 to 4, right, and this is 1 minus e to the power of minus, I will use first K 1 this multiplied by L2. Okay. So, now we will find out the values of L2 for different conditions. Okay. This plus we have A2, then K2 dash, then 1 minus e to the power of minus K2 dash multiplied by L2, okay, plus A3, then K3 dash, 1 minus e to the power of minus K3 dash, then L2 plus A4 by K4 dash 1 minus e to the power of minus K4 dash, then L2. So, big bracket close, then minus L2 by K is 0.648 multiplied by, we have Q load, which is already we have calculated. So, which is about 225 into 10 cube divided by AP, right. So, if we simplify it, then what we will have, so quickly I can write it. So, 82 minus 25 is 57, then we can take this part to this side and we can do the simplification, then what we will get is something like 34722.22 divided by AP is equal to, and if we simplify this, and this value will be about 339.85. Okay. Now, we will substitute, and these values are known to us. These values are known to us, and of course, we know this Kj bar is already we have done. Let us show what is this. kz dash is kj by cos of theta 2. Okay. So, that way we know what is kj here, and these values a1, a2, a3, a4, all the values are known to us. So, kj will be we have kj by cos of theta 2, which is nothing but kj divided by 0.8727. Okay. So, these values are already given. So, we can use those values. So, if we use those values, then this will simplify something like, first expression I will show, then later on we will straightway use our spreadsheet 237, this a1, and kj values will be something like 0.032 is the value for k1, and cos theta is 0.8727. Okay. Then 1 minus e to the power of minus 0.032 divided by 0.8727, and then we will have L2, right. This plus we will have A2 value is about 0.193. So, here it will be 0.45, K2 value divided by cos theta is 0.4727. Okay. And this will be 1 minus e to the power of minus K2 value is 0.45 divided by 0.8727 multiplied by L2. Okay. Then plus we will have A3 value is 0.167 divided by 3 divided by 3 is for K3 is cos theta 0.8727. Okay. And 1 minus e to the power of minus 3 divided by 0.8727. So, 3 is for K3, okay, multiplied by L2, plus we will have 0.179 divided by 35 divided by 0.8727. So, this 35 is nothing but K4 value, and this is A4 value. Okay. These are fixed. So, we are not taking the data from the air. This 35, and then we have 0.8727, then L2. Okay. L2, right. So, once we do the calculation, then what we will get, let us write the expression. So, it will be something like 57 plus 347.222 divided by AP, which is equal to 147.79. This is very, it's a long calculation. So, you can also try. So, if we now calculate AP, which is comes to be 3824.53 meter square. Okay. So, what we got when L2 is equal to 1 meter. Okay. So, in this expression we got the data, and then we have substituted L2 is equal to 1 meter. So, once we have substituted L2 is equal to 1 meter, then what we got, AP value is equal to 3824.53 meter square, right. So, we need to do the calculation for L2 is equal to 1.5 meter, L2 is equal to 2 meter, L2 is equal to 2.5 meter, then L2 is equal to 3 meter. Then we can find out at what depth we get the minimum area. Okay, so that means at that minimum area we will get the 18 kilowatt of power from this solar pond power plant. Okay, so now let us use spreadsheet here so that you can get the idea how this can be calculated, and we need to plot as well. Okay. So, I have done this calculation in this spreadsheet, and these values A1, A2, A3, A4 these are fixed. Okay. K1, K2, K3, K4 are fixed. Okay. Then we use A1 by K1, A2 by K2, A3 by K3, A4 by K4. Okay. Then we use that expression what we have just now made it. Okay. These are the expressions, and we have multiplied with it, then we got the data, right. Now, this calculation, if we substitute 1 here, L2 is equal to 1, then what happens? See, 2822, but in our calculation what we got is about 3824. Okay. So, this may be some kind of error we made during the calculations, right, and there might be some round of error and all, right. And if we substitute say 1.5, so maybe 1.5, see what happens. So, it is 3543.097. Okay. This is 3543.09 approximately it is 7. Okay. Then we will change the value to 2. Okay. And see what happens. We get a value of 3503.984. So, which is something like 3503.983617, okay, to be precise. And again we can change to 2.5. Let us see that what happens. 2.5, and it comes to be something like 3534.529. Okay. And again we can change the values of L2, which is equal to 3. Okay. Let us take 3 here and see what happens. So, we got a value of 3592.31 or so. Okay. So, if we take the values now and try to draw it, then see what happens here. Okay. So, vertical axis shows the pond area and this horizontal axis shows the depth in meter. Okay. So, with increase in depth, so this L2 means what? So, here, so this is the pond. Okay. So, this is the surface convective zone, then this is non-convective zone, and this is the lower convective zone. Okay. So, maybe I will surface convective zone. Okay. So, this L2 is nothing but this is L2. Okay. Here what happens? Minimum is found to be at L is equal to 2 meter, right. So, it is decreasing, and then minimum we found at 2, and then again it is increasing. Okay. And also sometimes if we are interested about process heat application, then we can calculate the collection efficiency, which is annual collection efficiency, right. So, depth we have, and then area we know, and then we can calculate annual collection efficiency. So, I can write it here how this annual collection efficiency can be expressed. Annual collection efficiency, so which can be expressed as eta C, maybe we can write, then Q load, okay, Q load divided by I into AP. Okay. Since we know the optimum values, maybe any values we can take, maybe for L is equal to 1 or 2 or maybe 3, then we can see what will be the value of annual collection efficiency. Okay. So, 225 into 10 cube, then we have 225.92 for I watt per meter square, and then if we consider L is equal to AP is something like 3503.98, then its collection efficiency will be 28.42%. Okay. So, that way you can calculate the collection efficiency, right. Now, let us go back again to the spreadsheet and develop the chart which shows the variation of annual collection efficiency with respect to depth. Okay. So, at L is equal to 1 meter, we get 26.05%, 1.5 meter we get 28.1%, and at depth 2 meter we get about 28.42%, what we have shown in the presentation. And if we increase depth to 2.5, then its efficiency decreases. See, at 3 it is 27.72. So, we have to go for this value, right. So, L2 is equal to 2 meter is the optimum value for maximization of annual collection efficiency as well as the performance of the solar plant. Okay. So, that is how it is shown here. Okay. So, it is starting from 1 and it is increasing, and then it reaches a maximum at 2 and then decreases. So, this depth is optimum, and this surface area is the optimum surface area for getting the maximum performance. Okay. So, thank you very much for your attention. Hope you have learned how to design a solar pond power plant, and this kind of problems are very, very practical. So, thank you very much for your attention.